Hello, dear students. I hope you have spent a good Eid time. I am preparing this lecture just after Eid. So my congratulations to every one of you. Okay, now what we are going to do today. We are now going to discuss yet another type of magnetic materials known as the ferromagnetic materials. Now what is ferromagnetism? It is in fact the spontaneous magnetization. This term spontaneous magnetization means that a magnetic moment even at zero applied magnetic field. Okay, in paramagnetic materials we have seen that until we apply the magnetic field, external magnetic field, we do not feel the magnetism of this material. Now, in ferromagnetic materials, it is a similar story that we do not feel magnetism at zero applied field, but there are magnetized regions already present in the substance, and we call them the magnetic domains. So our substance consists of several magnetic domains, and in each region of this magnetic domain the magnetic material is magnetized already, but at zero applied field, these magnetic domains are randomly oriented. Although they are highly magnetized, but they are randomly distributed so that we do not feel magnetism in the material. But as soon as we apply the magnetic field externally, then these domains line up in accordance with the field and show a very high magnetism, much higher than the paramagnetic substance. So this is the brief picture of the ferromagnetic materials. So we use the term spontaneous magnetization. Okay, now let me read through the text, but I will also explain during this reading. Wherever I feel, I will explain the underlying concepts so that you can understand the topic. Okay, let me now go to page number 444 of the textbook we are following. Okay, now this is the section 9.8 in the book by Ali Umar with title Ferromagnetism in Insulators. Now, ferromagnetism is the phenomenon of spontaneous magnetization. The best known examples of ferromagnets are the transition metals, iron, cobalt, nickel, etc. But there are other elements and alloys involved in transition or rare earth elements which also show ferromagnetism. Thus, the rare earth metals gadolinium and Dy and the insulating transition metal oxides like chromium oxide, they all become ferromagnetic under suitable circumstances. Ferromagnetism involves the alignment of an appreciable fraction of the molecular magnetic moments in some favorable direction in the crystal. So this is what I refer to as the domains, magnetic domains in the magnetic material. The fact that phenomenon is restricted to transition and rare earth elements indicates that it is related to the unfilled 3D and 4F shells in these substances. So we can say that in paramagnetic substances it is the unfilled S and P subshells, but in ferromagnetic substances it is the unfilled 3D 4F subshells which are responsible or which show ferromagnetic behavior. Ferromagnetism appears only below a certain critical temperature, which is known as the ferromagnetic transition temperature. So you must note that ferromagnetism is also related to a certain range of temperature for every substance. So for every substance there is a certain critical temperature below which ferromagnetism is indicated, and this temperature is called the Curie temperature. And as soon as we increase the temperature of the substance to above Curie temperature, then it simply converts into a paramagnetic substance. So ferromagnetism is vanished. So we can say that there are two phases of the substance. One is ferromagnetic phase, which is below the Curie temperature, and the other above the Curie temperature. In one phase it is ferromagnetic, and in the other phase it becomes a paramagnetic. This Curie temperature is different for different materials, for different solids. So you also must note that it is not every substance which show ferromagnetism, as we have just read that it is the rare earth elements and some of the insulating transition metal oxides. So it is not a general phenomena, ferromagnetism. It is seen in certain selected elements, few elements you can say. So the Curie temperature depends on the substance, but its order of magnitude is almost above 1000 degrees Kelvin. So it is well above the room temperature. So that's why even at room temperature in these substances we see the ferromagnetic behavior. And you can see table 9.6 here, which gives you this is the table I'm referring to. So in this temperature you see the Curie temperature written as TF, capital TF, in various elemental as well as the compound ferromagnetic substances. And there are other parameters, ms and mb, which I will talk about later. mb is the number of magnetrons per unit volume of this material, and the value is given for these materials. Okay. Thus, the ferromagnetic range often includes the whole of the usual temperature range region. Above the Curie temperature, the moments are oriented randomly, resulting in a zero net magnetization. So in this region, the substance is paramagnetic, and its susceptibility is expressed by this equation: chi is equal to C over T minus Tf. So where C is the constant, C is a constant known as the Curie-Weiss. This equation is known as the Curie-Weiss law, and Tf over here represents the Curie temperature. So the susceptibility has a singularity at T is equal to Tf. At this temperature and below, there exists a spontaneous magnetization because chi is infinite. So we can have a finite m for zero applied magnetic field. This equation, Curie-Weiss law, expresses the observed behavior of the ferromagnetic substances very successfully. The constant C is called the Curie constant, and Tf is called the Curie temperature. Equation 9.49 is the same form as equation for the paramagnetic substances, but chi is equal to n mu naught m square over 3 kT, which is the Langevin susceptibility, except that the origin of temperature is shifted from 0 to Tf. Figure 9.14 illustrates the applicability of the Curie-Weiss law to nickel, and we see a notable deviation appears only near the Curie temperature. Let me show you this graph. Okay, this is the graph in which the reciprocal of susceptibility per gram of nickel, which is a ferromagnetic substance, near the Curie temperature, which is almost 358 degrees centigrade, and the quantity P over here represents the quantity rho here represents the mass density. Dashed line represents extrapolation from higher temperature region. So we see that there is a certain deviation at the Curie temperature. Okay. Continuing with our topic, note that equation 9.49 predicts a divergence in chi as the temperature is lower towards Tf. This is an indication of the oncoming transition to ferromagnetic phase. Now, in the temperature range T less than Tf, we have spontaneous magnetization, which is referred to as saturation magnetization. This magnetization increases as the temperature is lowered, reaching its maximum value at T is equal to 0 degrees Kelvin. Thus, for the as the temperature is reduced, more and more dipoles line up in the magnetization direction, and table 9.6 gives the values of saturation magnetization in various materials. So this MS, which is in the second column, this is the saturation magnetization at 0 degrees Kelvin for all these ferromagnetic substances. Okay. So figure 9.15 shows the ratio of saturation magnetization at temperature T to that at 0 degrees Kelvin. That is Ms as a function of T over Ms at T is equal to 0 versus T over Tf for 3 ferromagnetic substances here, for iron, cobalt and nickel. Solid curve is obtained from Pi's theory, equation 9.55 for J is equal to 1 over 2. So ferromagnetism appears in both metals and insulators. It is simpler to treat the later materials, however, and therefore we shall limit our discussion here to the insulating materials, the ferromagnetism and insulators. We shall talk about ferromagnetic materials in section 9.10. Okay, now let us discuss the molecular field theory. I think let me finish here and we will discuss this theory in our next lecture. So you must also go through the same topic, the ferromagnetism, in the book by Kitto. Once you have gone through the text over here, I am sure that you will understand, you will follow whatever is written in Kitto, and you may get some new concepts when you go through Kitto. Okay, thank you very much.